Now we know that some atomic nuclei are unstable and they decay, they split apart, and when they do so, some of the stored nuclear potential energy in the atomic nucleus is converted into the kinetic energy of the fragments that are created by that splitting apart. So we get some thermal energy, we get some fast moving molecules coming out of that process. So how do we go about converting that into useful energy? That'll be what we're talking about in this part. Just as a reminder, this is from chapter 3, the summary of the amounts of stored energy in the chemical fuels. You can see it's a couple tens to a few tens of millions of joules per kilogram. The stored nuclear potential energy in uranium is 580 gigajoules per kilogram in natural uranium. That's 580 as compared to the natural gas number of 55. That's 10 times bigger than that, but giga means billion instead of mega or million. That's 10,000 times more stored energy in a kilogram of natural uranium compared to a kilogram of coal or a kilogram of natural gas. So that's super convenient. On the right, you see a picture of a coal train. Typical coal train is about 100 cars filled with coal, and a typical utility scale power plant will burn through 1 to 2 train loads per day of this. Near UCF, there is a fossil fuel burning power plant. It can burn natural gas or coal. Because natural gas is cheaper these days, it's mostly burning natural gas, but you can see the train tracks going up to it if you drive by there. Sometimes you can see these coal trains either full or unloaded. That's a huge amount. By comparison, you just need a truckload or so of uranium each year to supply the fuel for a nuclear power plant. So how does the nuclear power plant actually work? How do we get our energy from it? The type of reaction that we're talking about is nuclear fission. That's the splitting of a radioactive atom. And remember in the previous part, we talked about the half-life, and the atom has this sort of natural timetable that those atomic nuclei like to split. Well, we can trigger that splitting by hitting the nucleus of a radioactive element with a neutron. So that's what's depicted in the figure here. A neutron comes in, it strikes the nucleus. Now, this is not a single proton, that's representing the full nucleus, we'll see on the next slide. And that neutron destabilizes the nucleus, which then splits. And so when it splits, it splits into 2 different atomic nuclei and several neutrons. Those neutrons can then go on to trigger other atomic nuclei to split. So here's a fancier version of that same graph showing neutron-induced fission of uranium-235. That's the isotope of uranium we use in our power plants. So a neutron comes in, it comes into this big ball of protons and neutrons. And when it adds to that, it makes a very unstable nucleus. That's essentially a new isotope of uranium, uranium-236 instead of 235. That splits into 2 different atomic nuclei, a krypton and barium, with 3 neutrons. And the 5 products that are shown here have kinetic energy. And that kinetic energy came from the mass. Even though I've got the same number of protons and the same number of neutrons, if I put these 5 products, these 2 new atomic nuclei and these 3 neutrons on a scale and weighed them, they would weigh a little bit less than this uranium-236 nucleus. And that difference in mass is what is converted into the kinetic energy of these products. So that kinetic energy, then I can use that. It's kinetic energy of molecules. That's thermal energy. I can use that to heat water. So the fact that I also produce neutrons in that fission event means that the new neutron that comes out can be used to hit another uranium nucleus and cause it to split. So I can get a chain reaction. And of course, we have to moderate that to make sure that we don't have a runaway reaction, but the chain reaction is shown here. One neutron comes in, causes the nucleus to split, and if that split produces two neutrons, and each one of those neutrons hits a new uranium atom and causes it to split, then I get two more splittings that produces two neutrons each, and if those each produce two more, it can accelerate and go quite exponentially fast. And that's what happens in a nuclear bomb. It's unregulated runaway nuclear reaction where you have all of that energy released in a very short period of time. Obviously, for nuclear power plants, we want to keep that rate controlled. So in our nuclear reactors, we use put the fuel in rods. The rods are in water so that those products that come out heat the water, and then the water boils and becomes steam, which makes the turbine spin. But we also use control rods, and the control rods absorb some of those neutrons. So you can raise and lower the control rods as shown in the slide here, and doing so can slow down or accelerate the rate of nuclear reaction so that you can avoid having a runaway nuclear reaction, which leads to this the term meltdown that you may have heard of, where if they go too fast, then you have a runaway release of energy and it melts through the containment vessel. Nuclear reactors are built so that the default position of those control rods is down in between the fuel bundles to shut things down. So if we put this into a power plant, it looks like the schematics that we've seen before for coal burning or fossil fuel burning power plants. So if you look at this schematic, everything to the right of that pressure vessel and reactor core is essentially the same as what we would have if this were a coal burning or gas burning power plant. Steam goes into a turbine, spins it. That turbine is connected to a generator, which produces electricity. The cooler steam comes out, condenses into warm water, which gets put into a cooling tower to evaporate until it is cool enough to be safely reintroduced into the environment, and more water is then taken back in to complete the cycle. The only difference is instead of on the left having a chemical fuel being burned to boil water, now we have radioactive material radioactively decaying, and that produces thermal energy to boil the water in the reactor core. Just a different schematic of the same exact thing as on the previous slide, pointing out that so as those nuclear fuel rods react, you're gradually having less and less uranium-235 and more of those so-called daughter product atoms, barium and krypton in the example we saw earlier. And so as the concentration of uranium-235 goes down and the concentration of those daughter products goes up, at a certain point the fuel rods no longer are going to be able to have that chain reaction of nuclear reactions going on, and that timetable's a few years, and so the fuel rods need to be replaced on that sort of timetable, and the fuel rods in the end still have radioactive material in them. And this is where we get to the issue of radioactive waste, which we'll be talking about later in the module.